Hello again, everyone. This is Mr. Reeves back with you as we work our way through the Grade 8 CAASPP Math Practice Test. We've done 1 through 10, now on to 11 through 16. All right, so here we go. First problem says, which table of values can be defined by the function y equals 4x minus 2? So before we take a look at our choices, let's take a look at the equation we were given and remind ourselves what it means. Y equals 4x minus 2. What does that equation say? It says if you want to know what y is, take x, multiply it by 4, and subtract 2. So I'm going to go ahead and make my own table here. Let's get rid of the arrows. And let's just take a look here. Now, when we make an XY table, we can pick anything we want for X. So I'm just going to pick a few choices here. In fact, many times we math teachers have our favorite 5, I call them, -2, -1, 0, 1, and 2. And these are just some points that we like to choose because when we graph it, it gives us a couple negatives, a couple positives, and of course, 0. So again, if I want to find this value right here, what am I going to do? I'm going to do 4 times -2, take away 2. Well, 4 times -2 is -8, and -8 take away 2 is -10. So this point right here would be -2, -10. And then if I did the same thing, except this time putting in -1 for x, that would give me -4 minus 2, which is -6. When I put in 0, 4 times 0 minus 2 is 0, take away 2, which is -2. 4 times 1 minus 2 is going to be 4 minus 2, which is 2. We've jumped up into the positives now. And finally, for the last one, 4 times 2 minus 2. 4 times 2 is 8, and 8 minus 2 is 6. So if we take a look at the table, these are 1, 2, 3, 4, 5 ordered pairs that would make this equation true. And if we take a look each time, as the x went up by 1, the y's went up by 4. So when we go to look at the table that is correct, that's what we're going to be looking for. We're going to be looking for when the y's go up by 1, when the x's go up by 1, the y should go up by 4. We also should be looking for this point right here, which many of you know is the y-intercept, 0, -2. That's our value of b. And 4, of course, is our slope. Our slope is our change in y. Let me try that again. Change, or delta y over delta x. And we saw that that was 4 over 1, or 4. So as we look at these tables to see which one is correct, those are some things we're looking for. We could also simply plug in the x and see if we get the correct y. All right, okay, so let's go ahead and work through these tables. It says which one is defined by the function. Okay, so if we look right here, we have 0, -2. That was our y-intercept. So that one is a correct value, a correct ordered pair for this equation. But one alone doesn't work. Let's try, we did 2. 4 times 2 was 8, if you recall, and 8 minus 2 is 6. So that one also is correct. If we wanted to check one more, 4 times 4 minus 2, 16 minus 2 is 14. So just to let you know, once you find two that work, officially you are done because there is only one line or one equation that can make two ordered pairs that can contain two ordered pairs. But it's always a good idea to check three. Now, we've got our answer there. We're only allowed to choose one. We know that because these are circles and not squares. So if we were to go through and check, we would see that the other ones did not work. So it looks like I already actually chose the first one to be correct. So that table goes with that equation. That's the answer to number 11. Moving on to number 12. Rectangle ABCD, ABCD, there's rectangle ABCD, is rotated by 90 degrees clockwise about the origin and then is translated 3 units left and 2 units down to form a new triangle A prime, B prime, C prime, and D prime. All right, so let's take a look here. So this problem is a transformation problem. All right, transformations are when you take an object and you move it around according to a set of rules. And we do in 8th grade math, we do reflections, we do rotations, and we do translations. So the two that they are giving us in this problem is a rotation by 90 degrees clockwise, and then a translation 3 units left and 2 units down. All right, and by the way, order does matter usually when you do a transformation, so we're going to make sure we do it in the order that it is given. All right, so by the way, the question, we should actually read the question, shouldn't we? I read what the directions said to do, and it says, what is the length in units of line segment AB? So, A prime, B prime, excuse me. Now, one of the things that you should have learned or should be learning in 8th grade math is those transformations that I mentioned. We usually do translations first. And translations is another word for a slide, or a slide is another word for a translation. And then we have a reflection, and we often refer to a reflection as a flip. And finally, we have a rotation, and a rotation is a turn. These three transformations are called congruence transformations, or sometimes they are called rigid transformations. And the reason they're called congruence transformations or rigid transformations is because the original image we start with, which we call the pre-image, and our final one that we finish with, which we call the image. If you start with a pre-image and you apply any of these or any sequence of them, when you are done, what you have is the pre-image is congruent to the image. So that symbol right there doesn't mean equal, it means is congruent to. Now, equals, just to let you know, equals applies to numbers, all right? So equals is numeric, and congruent is geometric. Sometimes we get sloppy, like my writing. Sorry guys, doing my best here. Sometimes we get sloppy and we use the term equal for geometric objects, but congruent means that the object is exactly the same, just like equals means the numbers are exactly the same. So when I'm done, my final image, which they have called A prime, B prime, C prime, D prime, is going to be congruent to my pre-image A, B, C, D. So I could go through here and I could actually complete the process of making a 90-degree rotation. And a 90-degree rotation, a rotation is when you turn around the origin, and 90 degrees would involve us moving in a 90-degree at a 90-degree angle. So I could take that object and move around that circle, and you could see point B moving around that circle would end up right here at 4, 2. And 4, 2, my circle's just ever so slightly off. That point right there, 4, 2, would be, well, they called the final one B prime. So usually what we do is the first one would be B prime, and then the next one would be B double prime. So I'm going to call this one B prime. I'm going to go ahead and pretend that these are double primes. All right, because if you're doing two transformations, the first one will be prime and the second one will be double prime. And then I would take that point after rotating that point. Again, what I did was I rotated it 90 degrees clockwise. Then I would take that point and I would translate it 3 units to the left and 2 units down. So if I were to go 3 units to the left, 1, 2, 3, and 2 units down, I would end up down here. And that would be my final image point. Again, they called it B prime. We really should call it B double prime. All right, and then I could do the same thing with A. And then what I would see is that the distance from A to B, and the distance from A prime to B prime, and the distance from A double prime to B double prime, those distances are all the same. And the reason that they are all the same is because these objects are congruent. So there's really not a lot of work we have to do. If we want to know what is the length of A prime, B prime, then all we really need to know is what is the length of AB. Because the length of AB is not going to change as we go from AB to A prime, B prime to A double prime, B double prime. All right, so if you want to know the length on the grid, as long as we have a horizontal or a vertical segment, we can just count. So to get from A to B, it's 1, 2, 3, 4, 5 units. Or if you wanted to do it mathematically, it goes from -7 over to -2, and the distance between those, the absolute value of -7 minus -2, is going to turn out to be 5. So the distance of A prime, B prime is the same as AB. So the answer is 5 units, whatever those units happen to be. All right, that's question 12. Question number 13. Stephen claims that when you multiply two powers with the same base, the new exponent is the product of the original exponents. He uses the example below to support his claim. Drag a number in each box to create an equation that shows that Stephen's claim is incorrect. All right, so let's review some vocabulary first before we take a look at this. We have the word powers, we have the word base, we have the word exponent, and we have the word product. All right, so if I have 3 to the 4th power, we call 3 the base. That's the number that's being multiplied repeatedly. We call 4 the exponent, and the entire thing together is called a power. So even though we often say 3 to the 4th power, we're going to refer to the 4 as the exponent and the entire thing as a power. So we are finding the product. When you multiply, you're finding the product. So we are multiplying these together. And what Stephen is claiming is when these bases are the same, which they are, you add the exponents. Now, he claims actually not that you add, but that you multiply. And he says 3 to the second times 3 to the second is 3 to the 2 times 2, or 3 to the 4th. Seems to make sense, and it's an unfortunate example because this actually is the correct answer for the wrong reason. So let's use different numbers, not 2 and 2 like he used. Let's use 2 and 3. Excuse me. Yes. Our bases are 3, but instead of doing 3 to the second times 3 to the second, we're going to do 3 to the second times 3 to the third. All right, now, Stephen would claim that that is 3 to the 6th power, because he would say we need to do 3 to the 2 times 3, or 3 to the 6th power. All right, well, let's go ahead and check on this using the meaning of 3 to the second power. What does 3 to the second power mean? It means 3 times 3. And what does 3 to the third power mean? It means 3 times 3 times 3. And right here we have a multiplication symbol. So 3 to the second times 3 to the third is 3 times 3 times 3 times 3 times 3. Well, each of these dots means the same thing, multiplication. So what do I end up with? 1, 2, 3, 4, 5. How many? 5 threes. So 3 to the second times 3 to the third is 3 to the 5th, not 3 to the 6th. How do you get 5 from 3 and 2? You add, correct? 2 plus 3 equals 5. So Stephen is incorrect. Instead of multiplying, you add. That's why this one was unfortunate, because as you guys know, 2 plus 2 is the same as 2 times 2. So he got the right answer the wrong way. All right, so what did it ask us to do? It says drag a number into each box to create an equation that shows that his claim is incorrect. All right, well, why don't we just do the one we just did? What did we see? We saw that 3 to the second power times 3 to the third power is equal to not 3 to the 6th power. We're not going to go 6. We're going to go 3 to the 5th power. 3 to the second times 3 to the third is 3 to the 5th power. All right. Question number 14. David and Karen have a goal to reach 10,000 pages together by the end of the summer. David reads 80 pages every day. Karen reads 25% more pages every day than David reads. David and Karen agree that the model 180D equals 10,000 will tell them how many days it will take them to read 10,000 pages together by the end of the summer. They invite Rick to read with them to get to their goal faster. Rick reads 35% fewer pages per day than Karen. Which equation can be used to find how many days it will take David, Karen, and Rick to read 10,000 pages together by the end of the summer? Wow. This looks really, really complicated. That's a lot of words. So let's see if we can break this down and maybe make it a little more understandable. All right, so we're going to start with David. David reads 80 pages per day. So let me ask you, if it was just David reading and he had to read 10,000 pages, if we were going to write an equation, for David only. So he would be reading 80 pages every day, so 80 times D, and it would have to equal 10,000. So of course, if we want to know how many days it would take, we would do 10,000 divided by 80, and that would equal the number of days, D, to finish reading. All right, but now we have David and Karen. And they told us that the equation was 180D equals 10,000. Now let's talk about why it's 180. Well, how many of those pages are from David? 80. So how many of those would be from Karen? Well, 180 minus 80 is 100. So that means there's 100 for Karen plus 80 for David. So 180 is 100 of those are from Karen and 80 are from David. Now we know where that 80 came from. They told us that David reads 80 pages per day, but Karen reads 25% more pages every day than David reads. So I'm going to go ahead and make a diagram here. And I'm going to try my best to divide this into 4 equal parts. All right? And this is going to represent David. And hopefully you know that 1/4 is equal to 25%. So this is a fourth, and this is a fourth, and this is a fourth, and this is a fourth. Or this is 25%, 25%, 25%, and 25%. So we know that David is reading 80 pages per day. So if I had to fill these boxes, each with the same amount, and have it total up to 80, what would each box have to be? Well, there's 80 total, divided by how many? 4. And 80 divided by 4 is 20. So this box is 20, and this box is 20, and this box is 20, and this box is 20. So 25% of 80, again, 25% is equal to 1/4 is equal to 20, right? Well, what does Karen do? She reads what? 25% more. So I'm going to go over here and I'm going to tack on one more box. How much more does she read? She reads 25% more, but how much is 25%? 20. So how much does Karen read? Karen reads 80, the 80 David reads plus 20 more, which is 100. So that is where we get that 100 from, right there. That's where we get the 180, and they didn't ask us to do this, but if they asked us how many days it would take for David and Karen together, it would be 10,000 divided by 180. So that would also equal the number of days, only now it would be less days because we're dividing by a bigger number. All right, but now they're throwing in Rick. So now we're going to have David, Karen, and Rick. Okay, so we know the number is going to have to be bigger than 180. Just like 180 was bigger than 80. We know it's going to equal what? 10,000 pages. We know it's going to be something times D, but we have to figure out what that something is. Alrighty, so here we go. What does it tell us? It says Rick reads 35% fewer pages than Karen. 35% fewer pages than Karen. How many does Karen read? Karen reads 100 pages. Well, that sure was nice of them. Do you know why that was nice of them to have Karen read 100 pages? Because percent is always over 100. So if I were to ask you what is 35% of what Karen reads, it's 35 over 100 of what Karen reads. But what does Karen read? She reads 100. So 35% of 100 is 35. All right. If it had been a more challenging number other than 100 to find 35% of something, I'll call it X, what we would do, and I think we did this in a previous problem, actually I think that might have been for 7th grade, we would do 0.35 times whatever X was. But 0.35 times 100, hopefully you know when you multiply by 100, you simply move the decimal over 2 places and you get 35. All right, so Karen reads 100 and Rick reads 35% fewer. So to find out what Rick reads, I need to do Karen's minus that 35%, and 100 minus 35 is 65. So if we go here, what do we have? We have David reading his 80. We have Karen reading her 100. And we have Rick reading 100 minus 35, or 65. And if you add those together, you get 180 plus 65. 0 plus 5 is 5. 8 plus 6 is 14. Carry the 1. And we get 245D equals 10,000. And there it is. Choice number B. Wow, that was a challenging problem. But it sure was nice of them, like I said, to have Karen reading 100. That made our life a little bit easier. I didn't notice this before, but I happened to notice up here there is a calculator on this problem. So actually, even if they had made the numbers more difficult, we could have used this calculator. So I know we have the answer already, but if I pull the calculator up, if we had been asked to find 35% of a different number, is it not going to let us use the calculator? Oh, there it is. Not sure what happened. If you want to find 35% of any number, 0.35, let's say Karen had read, I don't know, 180 pages total, then we would have gotten 63. So the nice thing about a calculator is it really doesn't matter what number we put in. We can find 35% by multiplying by 0.35. All right, so look for that calculator and make sure that you are using it as needed. You don't have to use it just because it's there, but it's always a good idea, even if you do the math mentally or on paper, to check your answer with a calculator. All right, question number 15. Here we go, ladies and gentlemen. The graph shows Parker's distance from home over time. Based on the graph, determine whether each statement is true. Select true or false for each statement. Okay, so let's take a look here at this graph and let's interpret this graph. First, just looking at the shape of the graph, and then we'll actually look at some numbers perhaps if we need to. All right, so this is distance, and notice it's distance from home. It's distance from home. It's not a total distance. All right, it's distance from home. So right here, he's at 0. At time 0, his distance is 0. Where's he at right here? He's at home. He hasn't gone anywhere. Now, what is happening here as he moves along this graph? He is moving away from his home. The distance is increasing. As the time increases, the distance increases. So at this point right here, his time is now 5 minutes. And his distance, if we go over here, if this is distance in miles, this is a quarter of a mile, this is a half of a mile, this is going to be 0.375, which is halfway between, so 0.375 miles away from home. So for the first 5 minutes, he is traveling at a constant rate. He travels a total of 3/8 of a mile in 5 minutes. Now, what is happening right here? Two things are happening. Time is passing. We went from 5 minutes to 10 minutes. From 5 minutes to 10 minutes. So what happens? 5 minutes passes. But what about the distance? Did it go up? Did it go down? Or did it go straight across? The answer is, of course, it went straight across. What was the distance he started at? 0.375 miles. What was the distance he ended at? 0.375 miles. So what does that tell you? His distance did not change. So wherever he went, he decided to stop and remain there for 5 minutes. And then what happens? It goes down and he ends up back here. What is that point? That point right there is 15 minutes, right? 15 minutes. But what is his distance? If I go back over here, what's that pointing at? It's pointing at 0. His 0 miles from home. So if you are 0 miles from home, where are you? He's back at home. So he walked away again. He went 3/8 of a mile. He stayed there for 5 minutes, and then he walked back home. All right, so let's take a look and see what our choices are, which are true and which are false. All right, between 1 and 4, his distance from home is increasing. Is that true? Between minute 1 and minute 4, is the distance from home increasing? 1 and 4 is in that range, and the answer to that is true. All right, his distance from home is constant between minute 6 and minute 7. All right, so minute 6 and minute 7 is going to be in this range here. And in that range there, his distance isn't changing. It's staying the same. And that's what constant means. Constant means not changing. So that is also true. Parker's distance from home is increasing between 12 and 14. All right, well, 12 and 14 is going to be on this part of the graph going down here. And that distance is not increasing. He's going towards home. That distance is decreasing. So this one is going to be false. So true, true, false based on the graph. That gives us our answer to 15. And our last one for now, we're going to do question number 16. Mary is buying tickets for a movie. Each adult ticket costs $9. Each child ticket costs $5. She spends $110 on tickets and she buys 14 total tickets. Enter the total number of adult tickets and the total number of child tickets that she buys. All right, so here we go. So we have Mary. She is buying two different types of tickets, right? We have adult tickets that cost $9 each. And we have child tickets that cost $5 each. And we know two things beyond that. We know that she bought 14 tickets total. And we know that she spent, what's color I haven't used yet? How about orange? She spent $110 on tickets. Well, this actually sets us up for something we call a system of equations. What two things don't we know? We don't know how many adult tickets there are and how many child tickets there are. And in algebra, when we don't know something, we assign it to a variable. So the number of adult tickets, I'm going to call A. And the number of child tickets, I'm going to call C. And what do I know? I know that for every adult ticket that Mary bought, she spent $9. So 9A is the amount spent on adult tickets. Dollars for adults. Well, what is the dollar for the dollar amount or the total amount for the children going to be? Well, it's not $9 for them. It's only $5. And it's not 5A, it's 5C because C is the number of children tickets she buys. And what do we know this is going to represent? The total dollars for tickets. So this is how much she spent on adults. This is how much she spent on children. And this is going to be the total that is spent on tickets. Well, they total that the total that was spent on tickets was $110. I hope someone answers that. All right. So that is our first equation. I'm going to go over here and write it. 9A plus 5C equals 110. All right, but we also have another equation, all right? And it has to do not with how much money is being spent, but by the number of tickets. And this equation is actually much easier. The number of adult tickets she bought was A. Number of adults that were going, plus the number of children's tickets that she bought is C. And what would this represent then? This would represent the total number of tickets, right? Which we know happens to be what? 14. So that's our second equation. A plus C equals 14. So again, we have two equations here. The first equation has to do with the dollars being spent, and the second equation has to do with the number of tickets. And when you put those two equations together, you get something called a system of equations. And believe it or not, all we've done so far is set up the problem. Now what do we have to do? We have to actually solve that system. Now there's a number of different ways we could solve that system. We could graph these two equations and we could see where they intersect. That's called solving by graphing. We could use the substitution property where we solve for one of these variables and then we substitute what we got from either the first equation into the second one or the second one into the first one. In this equation, in this system, we'd probably substitute the second one into the first one. Or we can use the process of elimination, sometimes called the multiplication and addition or subtraction method, where we multiply one of the equations or both of the equations and then we add them or subtract them. And by doing that, we will eliminate a variable. Now, I've been teaching for a long time, and I got to tell you, out of those three methods, the most popular one of my students is the elimination method. And in the elimination method, and I usually recommend to add when possible, what we want is we want one of these terms to be the opposite of the other. So either we want the A terms to be opposites or the C terms to be opposites. And it really doesn't matter which one you do. All right, so I have 9 A's here. I can multiply this bottom equation by -9, and that would make this negative 9a. It would be the opposite. Or I can multiply this bottom equation by -5, and that would make this negative 5c. Well, since it's a little easier to multiply by 5s than by 9s, I'm going to go ahead and multiply this bottom equation by -5. And when I do that, I get negative 5a plus negative 5c equals, now 14 times 5 is going to be the same as 7 times 10, and I get negative 70. Now, just a quick reminder, when you multiply an equation by a constant, you do not change the solutions to that equation. So even though this blue equation looks different than that purple or magenta equation that we had, the solutions are all the same. All right, now I'm going to go ahead and rewrite my top equation, only now I'm writing it below it. And then I'm going to add those two equations together. And guess what? When you multiply by a constant, it does not change the solutions. When you add two equations together, you get a new equation that has the same solutions as they did before you added them together. Isn't that cool? So here we go. So 9a minus 5a, or 9a plus negative 5a, is going to give me 4a. The reason I made these opposite is so that when I added them together, they would be eliminated. 5 plus negative 5 is 0. So 5c plus negative 5c is 0c, so it's eliminated. And 110 minus 70. Well, 100 minus 70 would be 30, so 110 minus 70 is going to be 40. Whoops, let's go ahead and do that in blue. So I get the equation 4a equals 40. And it doesn't take a rocket scientist to know that A is going to turn out to be 10. So what did we just find? A stood for the number of adult tickets. What do we now know? The number of adult tickets is 10. But what also do we know? Mary bought 14 total tickets. Well, if 10 of them went to the adults, then that's right, 4 of them went to the children. So 10 adult tickets, 4 child tickets, and this should make both equations true. We already know it makes this equation true, right? So we know that 10 plus 4 is 14, but a good math student would go here and check this one as well. So what did we say A was? A was 10. 9 times 10 plus what did we say C was? C was 4. If we are correct, that should equal $110. Well, 9 times 10 is 90. 5 times 4 is 20. And 90 plus 20 is 110. So there we go. It works. So 10 adult tickets, 4 children tickets. I know that problem was very much involved, and there's other ways we could have done it. I know some of you are thinking, well, I could have just guessed and checked. And you're right. You could have just tried and guessed and checked, and you probably would have arrived there eventually. But the point of algebra is to eliminate guessing and checking. And when you're good at algebra, it can go much faster than guessing and checking. All right, well, that's where we're going to stop. When we come back next time, we'll start on question number 17. Thanks for watching.